Lately, I've noticed that college football stadiums all seem to have skyboxes. So my question is, for the 350 some days a year we're not having home football games, what are those used for? Classrooms? Conference rooms? Airbnb? I'm Professor Mark Hinders. I'm here in the NDE lab at William & Mary and I'd like to talk to you about pipe inspection. Pipes are everywhere, they're usually hidden. Eventually they're going to leak. It can be dangerous, it can be expensive, usually it's quite annoying. A few years ago, the water line at my father's house sprung a leak. The pipe that was used 30 years ago or so is a plastic that lasts about 30 years and then it springs a leak. And so he had the plumber come out and trench on the yard to run the new line to the house. And the plumber said to my father, now that I have the trench dug, I can lay 2 pipes in there instead of 1 that won't cost much more, and then if one leaks, you can just switch over the other one. My father said, you know, I'm 80. Last year, the water line at my house, which is in the same neighborhood just around the corner, sprung a leak. So I had the plumber come out and trench from the back corner of the yard and run a new line under the house. I just had him run one because they're using a new plastic now that hopefully will last longer than the old one. So pipes are going to leak. For metal pipes, the issue typically is corrosion. Whether it's on the inside of the pipe or the outside of the pipe, eventually the corrosion is going to reduce the thickness of the wall and the pipe will spring a leak. If it's a water pipe, that's an expense and a waste. If it's a sewage pipe, that's going to be a mess and might be quite disruptive. If it's natural gas, that can be quite dangerous. But if it's piping system and I don't know, something like an aircraft carrier, that's going to be a real serious issue. So one of the things that we've been working on is developing ultrasound techniques to measure the wall thickness in pipes in order to tell when the wall is thinned enough so that it might spring a leak. So you want to both locate the place where it's thinning, and you'd like to really know how much remaining wall thickness there is, because you don't want to go replacing pipes until just before they spring a leak. So here in Virginia, near William & Mary and Newport News, they build aircraft carriers, and aircraft carriers cost $10 or $15 billion to build. The life cycle maintenance costs on aircraft carriers is much, much larger than that. We expect aircraft carriers to last 50 years or more, and so the extensive piping systems sooner or later are going to corrode, and you really want to find those issues before the pipes spring a leak. So here is a sample piece of pipe that the apprentice shipbuilders made up for us. And what you see here is a length of piping, and the pipe is covered by lagging. This is the stuff that used to be asbestos. They assure me now it's not. Right? And what you see here, the yellow, that's the pipe, and here it's disappearing through a bulkhead, a wall. And the challenge is how do you find corrosion in pipes that are covered by lagging, but then also disappear through a bulkhead, perhaps into a compartment that you don't have access to. So what we do is we broadcast from a place where you have access to the pipe, mechanical vibrations in the megahertz range. These are, we call ultrasound. So ultrasound guided waves in the wall of the pipe that can go down the wall of the pipe, under the lagging, through the bulkhead, and then at some other place where you can get access to them, you can pick up those vibrations that end up the other side. And by analyzing those vibrations, those ultrasonic guided waves, you can tell where along the travel path of the pipe there's a problem, and ideally how serious it is. Cool thing about it is these mechanical vibrations will follow curvatures. So pipes have bends and whatnot, and these mechanical vibrations will travel from one place to another, follow the curvature through the walls, underneath the lagging. If it's an application where piping is buried under, say, a grade crossing or something like that, the mechanical vibrations can follow that, because you don't really want to have to dig up too much of the pipes in order to figure out where the problem is. You want to just dig up the place where the problem is, uncover the place where the problem is, and do the repair there, so the piping system can get back into service. So we had been developing Lam Wave ultrasonics for some years And we realized that if you consider a pipe as a plate that's rolled back up on itself, then Lam waves in the wall of a pipe is the same as Lam waves in, say, the skin of an aircraft or something like that. And so that's the idea. You're propagating mechanical vibrations, Lam waves, we call them, or sort of a generalized Lam wave, in the wall of a pipe. They'll go from one place to another, but they also, from, say, transducer A here to transducer B down there, they will propagate in complicated helical patterns round and round the wall of the pipe as they go to from one location to the next. In order to understand this fairly complicated physics, we build prototype systems in the laboratory here, scanners typically, so that we can explore the behavior. And sitting up here is a scanner that we built. You can see there's a transducer here. We can call this one A. Another transducer here, we can call this one B. These are connected up to stepper motors so that we can move those transducers to a bunch of different locations circumferentially, and that will mimic what you might do in the field, where you strap on a belt of transducers that go all the way around, and then with multiplexers you transmit from one and receive with the others and such. Okay? And so with an apparatus like this, we can mimic both the individual propagation from point A to point B. We also can demonstrate the multiplexing capability and explore how complicated that would be to make work. The other thing that we've been doing with these ultrasonic guided waves is tomography. We figured out that when you consider the pipe as a wrapped up plate, that a pair of circumferential transducer belts, all the various helical crisscross patterns of those, is a tomographic geometry. It's the same geometry, once you've unwrapped it, that seismologists developed. They call it cross borehole. And so this helical ultrasonic tomography, HUT, is a technique that we began developing some years ago to very carefully map out both the location and severity of thinning in the pipes. One of the important things about the ultrasonic guided waves is how fast they go depends upon the thickness of the wall. So if what you're trying to do is find a place where the wall has gotten a bit thinner, you look at the expected arrival time of either the straight traveling waves or the helical modes and compare when they should arrive to when they actually did arrive, and that difference in the arrival times allows you to map out the slowness, which the Lam wave dispersion curves allow us to correlate back to the thickness of the pipe wall. So helical ultrasonic tomography allowed us to make maps of the thickness of the pipe wall. Okay. We also figured out that if you, instead of unwrapping it when you unwrap the pipe, in addition to circumferential belts of transducers, you can consider transducers which are along the top line of it, called the meridian, and then that unwrapped geometry gives you a different way to do tomography. Because again, the Lam waves, the guided waves, are going to follow the curvature of the pipe wall itself. And so we mocked up a system in the laboratory. It's not fancy, and we're able to collect some data with scanned transducers in order to demonstrate proof of concept that this meridional tomography works for pipes. And then we also did it for larger cylindrical thin-walled things, storage vessels and things like that, pipes and tanks and such things. We also developed the helical ultrasonic tomography for inspecting gun barrels. The issue with gun barrels, Army howitzers, the issue is that not corrosion, but you get erosion on the inside, which affects the accuracy. And so we initially began developing this for the Army to put belts of transducers around the outside, and then at one point they said, no, we're going to put some heat shields on the outside, so we really need you to build a version of this that can go inside the gun barrel and inspect it that way. And so we built a really clever little robot that inchworms its way down inside the gun barrel, and then when it gets to the place where you care about it, it moves the transducers around in a similar geometry to this to be able to do the tomographic reconstruction, or to map out the change in wall thickness. And I don't have that robot to sell you because that device was a deliverable of the contract, but we did take a video of it inside a clear tube so you could see it, and that I think is just cool. Okay, so the tomographic reconstruction is a thing that we had developed for plate waves for aircraft inspection, and we adapted it for pipe inspection. Turns out that mathematically it's the same as long as you imagine plates and pipes to be rolled or unrolled version of the same thing. The guided waves follow that curvature, no problem. The guided waves can propagate good long distances in plates, pipes, and shells, and if you can automatically interpret the very complicated signals that you receive and understand that physics, then you can reconstruct a tomographic image of the parameter that you really care about, which typically is the remaining wall thickness and the area of the corrosion for the piping system. I'm Professor Mark Enders, Applied Science Department at William & Mary, as.wm.edu. Go Tribe. I mean Griffins.